Welcome to Demystifying Math. In this lesson, we're going to be graphing a quadratic equation. A function is considered to be quadratic if it is a polynomial of degree 2, or if it fits the model ax squared plus bx plus c. The domain of a quadratic function is all real numbers. The range will depend on the location of the vertex and the end behavior of the graph. Those are two things that we're going to try to find in this lesson. All quadratic functions graph as parabolas, or U-shaped curves. If the leading coefficient a, or the coefficient of x squared, is positive, the graph will open up on both ends. If it is negative, it will open down on both ends. You can easily find the vertex of a parabola by using the formula x equals negative b over 2a, where b is the coefficient of x and a is the coefficient of x squared. Let's look at this example. We have 4x squared minus 12x plus 5. We know that this is a quadratic function because it fits the model ax squared plus bx plus c, where a is 4, b is negative 12, and c is 5. Since the leading coefficient is positive, the graph will open up on both ends. We can find the x-coordinate of the vertex by plugging into x equals negative b over 2a. So the negative of negative 12 is 12, and 2 times 4 gives us 8. 12 over 8 in lowest terms is 3/2, or in decimal notation 1.5. We might also need to be able to find the y-coordinate of the vertex. So we're going to plug the 1.5 or 3/2 into the function and find our y value. So evaluating 3/2 into the function, we get out negative 4. So that means 3/2 negative 4 is our vertex. Sometimes the vertex is referred to as a turning point because it changes where the graph is increasing to decreasing or from decreasing to increasing. We already know that this graph opens up on both ends. So that means that 3/2 negative 4 will be the lowest point on our graph. And now we can find the range. Remember, the range is representing your values of y. So our lowest y value is going to be at negative 4, and then the graph's going to head up to infinity. So our range is from negative 4 to infinity. We often also need to find the zeros of a function, or where we have x-intercepts. We can do this by setting the function equal to 0 and factoring. So I factored into 2x minus 5 times 2x minus 1. Then we're going to take each one of those factors and set them equal to 0. So x is going to be 5/2 or 1/2, which means that we have zeros, or x-intercepts, at 5/2 0 and 1/2 0. We often also need to figure out where our y-intercept is, and we can do this by evaluating the function at 0. So plugging 0 in for x, we get out 5. That means that our y-intercept is at 0, 5. When graphing a quadratic equation, the essential points to plot are the vertex, the zeros, and the y-intercept. All of your quadratics will have a vertex and a y-intercept, but not all of them will have zeros. If there are no zeros, just plot 2 additional points to determine your graph. Since we have all of the essential points, we can now draw our graph. So I plotted the y-intercept at 0, 5, the x-intercepts at 1/2 0 and 5/2 0, and the vertex at 3/2 and negative 4. And then we know that our graph opens up on both ends. So starting at your vertex and going upward to draw your U-shaped curve. And just make sure that it goes through all the essential points that you found. Another thing that we want to keep in mind or to look for on our graph is whether it's increasing or decreasing, and on what intervals it is increasing or decreasing. So we're going to do that by estimating the slope of the curve by using a secant line. If the slope of the secant line is positive, then the graph is considered to be increasing on that interval. If the slope of the secant line is decreasing or negative, then the graph is decreasing on that interval. Let's look at two specific secant lines. We have one drawn from the vertex to the 0 at 1/2 0. Let's find the slope of that secant line. It appears to have a negative slope to it, but let's plug into our slope formula and figure out what our slope actually is. So we have y2 minus y1 over x2 minus x1. Our y values are -4 and 0, and our x values are 1.5 and 0.5. So we get a slope of -4, which seems to fit with the graph that we've drawn. Let's draw, we have another secant line drawn from the y-intercept to that x-intercept. So let's go ahead and find the slope of the secant line between those 2 points. So using 0, 5, and 0.5, 0, we get a slope of -10. And that secant line is steeper than the other one, but they both still have a negative slope to them. And you could probably imagine that if we put any 2 points on that side of the vertex, on the left side of the vertex, that the slope between those 2 points would be a negative slope. So if they have a negative slope, that means the graph would be decreasing on that interval. So in this case, we're decreasing on the left side of the vertex. Let's look on the right side of the vertex. So I've drawn a secant line from the vertex to the other 0 at 2.50, and we're going to find the slope of that secant line. And this time I got a +4, so that slope is positive, which means that the graph is increasing between those 2 points. And again, you can probably imagine that for any 2 points on that side of the graph, on the right side of the graph, your secant line would have a positive slope. So that side of the graph on the right side, the parabola is increasing. Parabolas have a line of symmetry that goes through the vertex, and that line of symmetry acts like a mirror. So if you have a positive slope on one side of the graph, you flip it over the mirror, or the line of symmetry, and you're going to get a negative slope on the other side. Let's look at that in detail. So I've drawn a secant line that's going on this parabola here, and I'm calculating the slope of that secant line. And what I'm going to do is move the secant line around the parabola, and we want to keep track of what this slope is. So at this point you can see that it has a positive slope to that secant line, and I'm just going to move it around a little bit. Notice that here it's very steep, but as I move it down toward the vertex, it's getting less steep. And you can follow it through and see it's still positive on this side. And we're going to close in on that 0 there. And you can start to see, it's getting more shallow, flatter. And as we go down toward the vertex, it's still positive on this side of the vertex, but less steep. Now, if I switch to the other side of the vertex, now my secant line is completely to the left of the vertex, you can see that the slope is negative. So on this side, we now have a negative secant line slope, and it's going to continue to be negative. Now as I go upward, it's getting steeper and steeper, so we have a bigger number for our slope. So what we saw was that this parabola is decreasing, or has a slope of a secant line that's negative, for all x values from -infinity to 1.5, and then it's increasing on the other side of the vertex. So from 1.5 to infinity, it's increasing, or you could say that the slope of the secant line would be positive. Just keep in mind that this slope is going to depend on whether the graph opens up or opens down. So if we flip the graph upside down, it's going to change which side is increasing or decreasing. And you'll always need to find your vertex in order to decide which side is increasing or decreasing from what point to what point. And also just kind of look to see whether it's going from -infinity and to what x value it's going to. Don't use y values when you talk about increasing or decreasing. Okay, thank you for tuning in to Demystifying Math.